We now turn to Chapter 9, looking at truth functional logic, finishing up our look at deductive logic. The objectives for Chapter 9 are these. First is to understand the basics of truth tables, which are used to test for validity, and the truth functional symbols, the various connectives and variables. Also, just like with categorical logic, truth functional logic is a separate language, an artificial one, and we'll learn to translate from normal English into truth functional logic using claim variables and the truth functional symbols and eliminating all things we consider, normal words. Next, our kind of end goal is to test for validity, and with truth functional logic, in this case, we do this by building truth tables and use these to test for validity. So learn how to do that. We'll learn to evaluate truth functional arguments, and we'll be looking at some of the common argument forms, both good and bad. And then, as I mentioned before, the end game is testing for validity to see if an argument is valid or invalid. So, without further ado, into the truth functional logic. So, truth functional logic, as the name clearly states, is a logic system which is truth functional. So what does that mean? Well, it means that it's a system of logic that specifies the logical relationships among truth functional claims. And of course, this definition takes us into a circle because we define truth functional with truth functional, but we can fortunately clear this up. So this logic deals with the logical functions of particular terms. In English, we would present them as not, and, or, if then. And a truth functional claim, to break the circle, these are claims whose truth values depend solely upon the truth values of their simplest component parts. That is to say, the function of any truth functional claim results from the truth values of the parts in terms of how they, if you have multiple parts, in terms of how they are connected. And we'll see all this laid out in the truth tables, etc. So what is truth functional logic used for? Well, it is foundational in set theory. Some philosophers claim correctly that it's the foundation of mathematics. And getting into sort of, very practical applications, it's the model for electronic circuits. If, for example, you were wiring a house and setting up light switches, you would use truth functional logic, although typically as an electrician, you wouldn't say, I'm doing some truth functional logic, unless you also had some experience in philosophy, but that's how it works. And of course, computers are based on, 0, 1, on, off, instead of true, false, but computers, at least the common ones, roughly speaking, are truth functional machines. So no truth functional logic, there would be no Facebook, Xboxes, etc. It's also useful for analyzing arguments. Essentially kind of the more philosophical aspect of truth functional logic, which is looking at arguments to see if they're valid or invalid. So what are the benefits for learning truth functional logic? That is to say, why, aside from exams, assignments, and quizzes, why bother? Well, the first thing is learning about the structure of language. Although truth functional logic is technically an artificial language, as opposed to one that just kind of, arose from people's natural activities, it does, of course, match up mostly with natural language. And so we can understand the structure of our natural languages, in part by looking at truth functional logic, with some exceptions. Second, it's also useful as sort of a entry into precise systems of symbols. And it's, not a mathematical system, but it's a kind of an entry into that kind of formal uses of symbols. And it's kind of a good foundation for getting into computer programming, because essentially all computer programming languages would ultimately, all the ones, common ones, ultimately are founded on truth functional logic. And of course, it can also be useful for being clearer in ordinary language. Again, even though truth functional logic is a precise system, it's also useful for clarifying what one is saying. And another pragmatic application is standardized test, and most specifically the LSAT, which is, as I mentioned previously in class, essentially is a philosophy test. And the game section is truth functional logic puzzles. So looking at the truth functional symbols, so here's the language we're working with. And as I mentioned before, this is a language, and so it's got its own rules, etc. So this language is built out of claims, which are symbolized by what are called claim variables. And a claim variable is just a letter that stands for a claim. It can be any claim. If you're familiar with mathematics, variables are used in mathematics to stand for any particular number. And the same thing is here, except the claim variables stand for claims. So the claim variable P, and the most commonly used ones are P, Q, and R. The claim variable P could stand for anything. It could stand for something like today is Monday, or it could stand for waffles are delicious, whatever you wanted to stand for. Now, a critical assumption in truth functional logic, at least the version we're looking at, is the assumption that any claim is either true or false, but not both. So it's binary. It's either on or off. There's no levels or degrees. And so the assumption is any claim is either true or false, and not both. It can't be both true or false. Now, there are other logics that have complexities to them, but we're sticking with the most basic of truth functional logics, which is any claim is either true or false, but not both. Now, the way we explain or understand the connectives is through the use of truth tables. Kind of going back to our look at Venn diagrams, we first looked at Venn diagrams with just the two circles, the S and P, to look at our four sentence types. And so we'll also look at the truth tables for truth functional logic, initially to define our how our connectives work. So what is a truth table? Well, a truth table, to be, I guess interesting perhaps about it, it's a map of possible worlds, all the things that could be, on the assumption that any claim is either true or false. More formally, and probably less interestingly, a truth table is a table that lists all possible combinations of truth values for the claim variables in a symbolized claim or argument, then specifies the truth value of the claim or claims for each of those possible combinations. Or again, to put in more interesting terms, it is a map of all possible worlds, what could happen given what you're talking about, on the assumption that any claim is either true or false. So let's take a look at a very simple table. So the simplest table of all would be looking at one claim variable, in this case P. And again, tradition is such that philosophers use P, Q, and R, and then you just keep adding more letters until you've taken care of what you need to take care of. So the two options, assuming any claim is true or false, but not both, for P, the options would be a scenario where P is true and where it's false. An example of a practical application of this in everyday life would be a simple light switch. A simple light switch is it's a variable. In a sense, it has two states, on or off, and that shows the possibilities. The light is on, the light is off. And again, this lays aside things like dimmer switches. Now, obviously we can't do like a whole bunch with just one variable, but we can do light switches, or on-off switches. So what about having two variables? Well, the two variables, and the beeping in the background is the power keeps getting knocked out for some reason, and that's the backups that are kicking in. Fortunately, saving this recording. So if we have the two variable table, this will show the possible combinations. So this is just variable P, variable Q, and again, this is not really showing anything except how the variables work. So the table here is something we'll generally never use again once we get beyond just defining the connectives, shows the possible combinations if you're considering two variables, just happen to be P and Q. And so the table shows all the possible combinations, the scenarios that can occur, assuming every claim is either true or false, but not both. And so you have both being true, P being true, Q being true, P being true, Q being false, P being false, Q being true, and both being false. And this table is filled in with a purpose, and any table that is a two-variable table with P and Q will always look like this, as we'll see in the future. So in terms of how you would fill in, in terms of like why it was filled in this way, the reason is this. It shows all the possible combinations, and here's how you do it. You start off looking at the column furthest to your left, and you'd alternate true, true, false, false, and then you head to the right, alternating true, false, true, false. You can also do this, and we'll see this getting more complicated. We have more variables. You could always start off to the table column furthest to your right, alternating TF, TF until you run out of rows, and then head to your left, alternating pairs, TT, FF. And what this does is this ensures that all possible combinations occur. And this could show the combination if you have, two light switches. You could have both lights on, one off, one off, one on, or both off. And again, these single variable and two variable things are just to show how the trues and faults, fill in. These aren't, beyond that, they're not used to do really anything. So what are our connectives? Well, the connectives work as they do in, English mostly, in that they combine, simple parts to make more complex parts. Now, our first connective is called negation. And you may think, how can this be a connective? Because it's not connecting two things. It's just kind of stuck on typically just one thing. But it's called a connective. So negation corresponds roughly with the word not in English, and it's going to be false when the claim being negated is true, otherwise it's true. So it works exactly like not in everyday English. If a claim is true, and if you say, not that claim, it would be false. So if the power is on now, the claim the power is not on would be false, and vice versa. This is symbolized by the tilde, that little squiggly thing. Sometimes, of course, people just use the negative sign, and as long as you're consistent, it really doesn't matter what you're using. So it's applied to claim variables, and of course, any claim is either true or false, but not both. And so when you negate it, it just reverses. True becomes false, false becomes true. So the simplest truth table for this, and this just illustrates how negation functions, what it does. As we'll see, you can have much more complicated tables with all kinds of stuff going on, but this is the simplest version of negation. So you have the variable P, one variable, and then you have the negation of P, not P. And it just reverses, true becomes false, false becomes true. So if P is true, not P is false. And if P is false, not P is true. And again, it works just like normal everyday English. When you negate something that's true, it becomes false. And if you negate something that's false, it becomes true. So negation essentially says, hi there, I'm negation. Whatever I'm negating, if it's true, then I'm false. And whatever I'm negating, if it's false, then I would be, as a negation, true. So that's negation. Our second connective, and this is what you more commonly think of as a connective because it actually connects things, is conjunction. And this is corresponds pretty much with and similar words in English. And a conjunction would be true only if both of its conjuncts, both parts, are true. Otherwise, it's false. And this works, exactly like we use and in everyday English. Now, of course, we have other phrases besides and that stand for and, but even though and other phrases can be used to form conjunctions. In this particular book, the symbol used for a conjunction is the ampersand, which makes sense. That's kind of the standard and symbol. Some books use different symbols. They might use a big dot, or they might use what looks like an upside down V, but as long as the symbol is used consistently, again, it doesn't really matter because symbols are all arbitrary. So what does a truth table for a conjunction with two variables look like? Well, in this case, we're combining P and Q. And again, this is just like an illustration. This is not the only way you can use P and Q. It can be done much more complexly. But this is just to define the connectives, to show how they work in the simplest situation. So we've got our two variables, P and Q, and we have our conjunction, P and Q. Now you might recognize the P and Q parts, the two columns for the P and the column for the Q, from earlier. And of course, it fills in as it always does. So it's going to be for the Q column, assuming a two-variable table, true, false, true, false. The P column for a two-variable table will be true, true, false, false. It's always going to be like that. So conjunction is true. A conjunction is true when both conjuncts are true, otherwise it's false. So P true and Q true, true. But in the other cases, P being true, Q being false, it's false. P being false, Q being true, also false. And of course, not surprisingly, false and false is false. And this corresponds to how we use the conjunction and in everyday English. So if there is a party and I promise to bring hot dogs and buns, and I show up with both hot dogs and buns, I've told the truth. If I show up with just hot dogs and no buns, I've not told the truth. If I show up with no hot dogs and just buns, I've also not told the truth. And if I show up with nothing, I've obviously not told the truth. So conjunction works just like and in normal English. Now disjunction. Disjunction is essentially or, but a particular type of or in English. There are actually two types of or. So a disjunction, the type we're using, is false only if both disjuncts, both the parts, are false. Otherwise it's true. So it's true when one or both of the parts are true. This is known as the inclusive or, that is the standard used in logic. There's also what's called the exclusive or, which you can do a truth table for, no problem. And it's the or typically of things like sports and sides with food. To illustrate with sports, if you have two teams playing, say the Red Sox and the Yankees, either the Red Sox win or the Yankees win. Both can't win. One wins or the other. Exclusive or. Also, the logic of sides, the or of sides, when you order, say, like a hamburger or a sandwich or something, typically you get a choice of one side. And you have multiple ones to choose from. And, obviously you can buy more sides, but you have a choice of one or the other or the other or the other. So if it's like fries or macaroni and cheese or coleslaw or, a baked potato, you can pick one of those because it's the exclusive or. It's one or the other, but not both. But again, the logic or is commonly used is inclusive or, one or the other or both. So the truth table looks like this. Once again, we have our old friends P and Q, and we have our disjunction, which is symbolized by the V, just because. And again, this is just an arbitrary symbol pick, so that's why it's that. So it's going to be true except when both parts are false. So when P is true and Q is true, P or Q is true. When P is true and Q is false, they're still true. If P is false and Q is true, still the whole thing, P or Q is true. The only time it's going to be false is when P is false and also Q is false. And this corresponds to how we use the inclusive or in normal English. So, for example, if there's a party and I say, I'll bring pie or cake, and I show up with pie and cake, P and Q are both true, then great, I kept my word. If I show up with pie but no cake, well, sad, but not the saddest, I've kept my word. If I show up with, one and not the other, I'm still telling the truth. The only way I'd be lying is if I promised pie or cake and I showed up with neither pie nor cake. In that case, the disjunction would be false. Our final connective, which is the most the most complicated one, is the conditional claim. And the conditional claim consists of, it's an if-then claim. It consists of an antecedent and a consequent connected by, if-then. So in an if A then B claim, A would be the antecedent because it comes first. In if A then B, B would be the consequent because it comes second. Now, this is just, terminology. There's nothing special about this. It's just that they call the thing first the antecedent, and then what follows the consequent. Ante before, consequent, essentially after. And this again assumes it's in standard if A then B form, and as you can, as we'll see, you can have conditionals where the order is, a bit different. So a conditional claim is the one that's on sort of first looking at it may seem a bit, counterintuitive or confusing, but if you think about it, it actually makes sense. So a conditional claim is false if and only if its antecedent is true and its consequent is false. And we'll see the table for this in just a moment. Now, it kind of corresponds to if-then in English, but not exactly. It's, essentially kind of even though it roughly is like if-then, it's a made-up connective. And the symbol for it is, typically the arrow there. Some books use the horseshoe, but that sometimes falls out of favor because the horseshoe symbol is also used in math, and so to avoid confusion. But again, all these symbols are arbitrary, so what they mean, depending on what people say they mean. So here is the truth table for the conditional. So as always, we've got our P, we get our Q, and always fills in the same way. If you're a two-variable table, it's always going to look like that. So now we have our conditional. And the conditional is such that it's going to be true except when the antecedent is true and the consequent is false. So at first this will seem to make sense, and then it'll seem a little odd, but then after an explanation, it should make sense again. So if P is true and Q is also true, then the conditional is true, which is hardly surprising. If the antecedent is true and the consequent is false, also hardly surprising. Now, what might start getting surprising is that if the antecedent is false and the consequent is true, the if P then Q is true. And this may seem the weirdest of all. If both P and Q are false, the whole conditional is true, which may seem kind of bizarre. How can, two falses make a true? But here's the explanation that'll hopefully make sense. You can think of the conditional as like a promise, essentially, that if one thing occurs, then the other thing will occur. To use a concrete example, imagine a professor says that if it's their office hours, then they'll be in their office. Obviously barring like unusual circumstances, etc. So suppose you go by, it's their office hours, they're there. The antecedent's true, the consequent is true. Well, they're telling the truth. They haven't been shown to have lied. Suppose you go by, it's their office hours, but they're not there, and they never show up. In that case, their claim that if it's their office hours, they'll always be there would not be true. Now, suppose you go by, and it's not their office hours. You go by, say, well outside their office hours, and they're there. Well, you've not shown that they've lied. It'd be weird to go to the dean and say, this professor's, lied about office hours. And he would say, that's terrible. What did they do? Well, I went by their office outside of their office hours, and there they were, plain as day. And of course, that would be silly. So this doesn't show the person was lying. That is to say, the conditional has not been shown to be false, so it's considered true. Now, the last case, again, would seem the weirdest, but it actually makes sense. Go back to the example, if it's true that if it's their office hours that the professor will be in their office, suppose you go by, it's not their office hours. You go by at like 3 a.m. Saturday morning, and they're not there. Well, have they been shown to lie to you? Well, imagine, someone goes to the dean and says, I was in the building at 3 a.m. on Saturday. I looked in the professor's office. They weren't there. Well, that would be obviously kind of odd, but it wouldn't disprove their claim. So that's how you could have both parts being false and the conditional being true. Now, in terms of like dealing with this, the easiest way is just accept that's how it works. That's logically how it works, and just fill in the T's and F's as appropriate. If you need an explanation, we can go with the one I just gave. It's essentially a promise, and the only time a promise is shown to be a lie is if the condition of the promise is fulfilled, but it's not delivered on. So that takes care of our connectives. Now, as I mentioned, we can have things that are somewhat more complicated. Here's something that's a little more complicated, but not like super complicated. So this shows how we can get beyond just our sort of example truth tables, illustrating in the most basic ways how the connectives work. And this allows us to have, combinations like this. So suppose we wondered that, the truth conditions for a claim like if the money is not paid, then Sam will be fired, or any other like negation than consequent. Well, the way you do it is like this. As always, the P column and the Q column get filled in the same way. In this case, we have not P, and what negation again says is, hi there, I'm negation. Look at what I'm negating and negate it. True becomes false, false becomes true. So when P is true, not P is false, and when P is true, not P is still false, and when P is false, it's not P is going to be true. So it fills in that way. Now, in our sort of defining simple table, we had if P then Q, but we can easily do P then Q, because the conditional says there, hi, I'm a conditional, look at the column for my antecedent, whatever that might be, and then look at the column for my consequent. And if my antecedent is true, whatever it might be, and my consequent is false in that row, then the whole conditional is false. Otherwise, it's true. So in this case, we're looking from not P to Q. So false antecedent, true consequent, the whole thing is going to be true. Not P then Q will be true. Not P is false, Q is false. And again, this may seem odd, but if not P then Q is true, then we have both of them being true. Not P is true, Q is also true, so the whole sentence, not P then Q, is true. And then in the last case, we have the antecedent, not P being true, and the consequent being false, and so it meets the condition of being false. So in that case, not P then Q would be false. And that's a fairly simple combination table. Now we can also have more than two variables. In theory, there's no limit, but beyond about 3, the tables start getting, needlessly big. So this is what a 3-variable table would look like, and using P, Q, and R. And again, P, Q, and R are just arbitrarily picks. They're just used by tradition. So the way you fill in the table, and again, this table really doesn't do much of anything besides showing how you'd fill in P, Q, and R in this basic table. So you start off, in the column furthest to your right facing the table, alternating singles, TF, 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 all the way down. Then you'd head to the left, and then you'd alternate pairs, TT, FF, TT, FF, all the way down, and then you keep heading to the left, alternating groups of 4. And then it would, if you had a bigger table, this would obviously be bigger. And you can see the table starts getting really big really quickly. and would start growing too much. So how do you know how to construct a table, like a slightly more complicated one? Well, here's the formula for table construction. And each time we build a table, we'll go through how to build it. So one question, of course, is how many rows do you have to have? Now, this is the easiest one to determine because this is always going to be following this formula. The number of rows, we'll call that R, equals 2 to the n, where R is the number of rows in the table, and n is the number of claims. So when you looked at our one variable table, it's 2 to the 1, 2. So you have, like with the P, just the P table was true false. When you went to 2 variables, it grows to 2 to the 2, 4. And then when you get to 3 variables, it's 2 to the 3rd and 8. And as you can imagine, it just keeps expanding and expanding. So when you build the table, as I mentioned before, what you do is you start off, for the columns, for the variables, and this is only for the variables, you'd go off to the farthest column for a variable, to your right, alternating T and F, and then move to the left, alternating pairs, then move to the left, alternating, groups of 4, then you'd go, if the table keeps growing, you'd go, to the next one, alternating 8 and 8, and then so on. Now, the top half of the leftmost column will always be, all, T's, and then the bottom will be all F's. So always look that way. And as I mentioned, tables can get ridiculously big pretty quickly. A bit more on constructing tables. So, in order to do the table properly, standard truth tables won't have any English words on top of them. You have to have just claim variables, connectives, and parentheses. They're the only things that can be included in them. So no words, etc. And this is standard symbolic form. And it'll only have those components: claim variables, connectives, and parentheses. So here's an example, simple example of symbolizing something. So if Paula goes to work, then Quincy and Rogers get the day off. And we'd symbolize this as if P, then Q and R, with the parentheses around Q and R. Now, the reason why we use parentheses in logic is the same reason why we use them in math, because where you put the parentheses in math does make a difference for the calculations. And likewise for logic, where the parentheses are, it makes a big difference. So when we have these compound claims, so in this case we have something obviously more complicated than our simple definitions for the truth tables, because in this case we've got 3 variables all in one claim. Now you may be wondering, given what we only looked at 2 variable tables, how can we handle, in terms of the connectives, how do we handle these more complicated ones? Well, the fortunate thing about truth functional logic is it is exactly what it says it is. Namely, the truth value of a compound claim depends entirely on the truth of its parts. So you can break down the table, or break down the claim piece by piece to get at the simplest bits, and the truth value of the whole thing depends on the truth of the parts. Now, of course, if the parts are compounded, the truth value of those parts depends on their simpler parts, breaking it all the way down just to the claim variables. So, when you build the table, you'll have what they're called the reference columns, and those are the ones that hold the claim variables. By convention, they're always off to the left side of the table, and this is just to make things, easier. You could, go wild and put stuff all over the place, but it would be, kind of needlessly confusing and complicated. And so just out of convention, just like, picking a side of the road to drive on, you just, stick with where it goes. So the variables always live on the left-hand side of the table, just again for a matter of convention, and it it makes more sense. It's easier to do. And so the table will give us a truth functional analysis of the claim. So here's a 3-variable table that's more complicated. So this is the, if Paula goes to work, then Quincy and Rogers get the day off, symbolized as if P, then Q and R. So the table would assemble like this. It's a 3-variable table, so our 3 variables live off to the left-hand side, and tradition is that you put them in alphabetical order, although, again, you could go against tradition and like do them in different order, etc., but that would be, confusing to anyone who's using the standard approach. So out of convention, it's P, Q, and R, alphabetical order, just because tradition, and easier. So you start off with, first filling in for the variables, and the R column is furthest to the right, and so you'd fill in alternating, singles, TF, TF, until you run out of rows. Then you head to the Q, true, true, false, false, true, true, false, false, and then you go to finally at last to the far left with the P column, and that would be 4 T's, 4 F's. And again, we know how many rows to have because it's always going to be 2 to the n, so 2 variable, or in this case 3 variables, 2 to the third, or 8. And tables will always have, 2, you'll go like that, 2, 4, 8, 16, and so on. You won't have truth tables with like uneven, odd numbers of rows. You won't have like a 5 row table, etc. So then we go to fill in the other parts, Q and R, and we need to have the Q and R there because in order to do the column for if P, then Q and R, we need to know the possible truth values of Q and R. So we break off the simpler bits. We essentially are breaking it down. So P, then Q, R breaks down to Q and R, and of course Q and R breaks down to Q and also the variable R. And so when you're setting up a table, you got to have every variable gets its own column. Every claim gets its own column, and then you have to break down any compound claim to its simpler parts. And with each breakdown, you need to get another column for that part, and then you keep breaking it down until you're down to the claim variables. Once you get down to the claim variables, you don't duplicate. You wouldn't duplicate them because you only need the claim variables there once. You don't repeat. Don't duplicate anything because even though I guess you could, but it would look identical. And if they don't look the same when they're identical, something has gone wrong. So filling in the Q and R, this may look more complicated because instead of our usual 2-variable table with just P and Q, we now have the 3-variable table with Q and R. And so the way we fill it in, though, we just follow the truth functional, meaning. So a conjunction is true except when one or both of the parts are false. So we go down row by row, looking at the Q and R columns and see what goes in the Q and R. So when they're both true, their Q and R is true. When Q is true and R is false, Q and R is false. When Q is false, R is true, so Q and R would be false. And if they're both false, obviously false. When they're both true, it's true. And then, again, when Q is true, and we see that R is false, Q and R would be false. And then when Q is false, and also R is false, then Q and R would be false. And when they're both false, then it's false. So even though, again, it's more complicated because we have more rows and we have Q and R rather than just P and Q, these steps are still the same. It says, hi there, I'm conjunction. Look at what I'm conjoining, the two columns. If you see a T in both of them, I'm true. If you don't, I'm false. Now, the last column, P then Q and R, looks the most complicated. So how would you know what's going on here? Well, the fortunate thing about truth functional logic is anything in parentheses, you can think of it as metaphorically contained. Think of it as like, oranges or apples like in a bag, or parts in a box. So if you have a bag of oranges, it's one thing. It's a bag of oranges. I mean, it's got a lot of oranges in there. Or think of like your backpack. You can have a lot of stuff in there, but it's one item. And the parentheses are just containers. So P, then Q, and R, the antecedent is P, and the consequent, even though it's complicated, whenever something's within parentheses, it just functions as one thing. In this case, it's Q and R. So to tell the truth value for if P, then Q and R, you look at the P column for the antecedent, and then you look to that's why we have the Q and R column there, the Q and R column for the consequent. And if P, then Q and R will be true, except when P is true and Q and R is false. So in our first row, P is true, Q and R is true, so if P, then Q and R is true. Then in our next row, we get P being true, Q and R being false, so if P, then Q and R would be false. And then, of course, we can go down the table row by row by row and see in the cases where the antecedent is true and the consequent is false, the whole thing is false. And you might notice that for the last four, P, then Q, and R, it's going to be true in each of these cases. And the reason why is because in a conditional, when the antecedent is false, it doesn't matter what the consequent is, then the whole conditional will be true. So P is false, 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 and then false. And so, not surprisingly, P, then Q, and R is going to be, by the definition of the conditional claim, it's going to be true in each of those last four rows. So that's the sample 3-variable example table with some complications going on. Our next concept is that of truth functional equivalence. So what is that? Well, truth functional equivalence is this. Two claims are truth functional equivalent means they have exactly the same truth table. Informally, and kind of incorrectly, you can say that two claims are truth functional equivalent means they mean the same thing. They say the same thing just with different words. Just like you use an analogy, you can say a dozen or 12, they mean the same thing. More formally, of course, for two claims to be truth functional equivalent means that they're true under exactly the same conditions and false under exactly the same conditions. And so when you construct a truth table for the two claims, if their columns are identical, and of course the truth table has been assembled correctly, then that means that they're truth functionally equivalent. So why is this useful? What does it mean? What's it done for? Well, one sort of, I guess, way to use it in terms of writing is if you keep kind of like saying the same thing but want different words, you can use things that are true functional equivalent as a matter of writing. Another example is if you want to say something, again, this is focusing on writing rather than doing like logic stuff. If you want to say something simpler, you might take something like that would be complex or confusing, something with like negations and stuff in it. And if you can find something true functional equivalent, you could say it in a clearer way. Or on the side of evil, one thing that could be done on, say, a standardized test is to take something that would have a clear meaning, find something that is true functional equivalent, especially like in the logic games, and present it the thing that's much more confusing. And again, people tend to find negations and conditionals confusing, not always, of course, but tend to be more confusing. So if you want to make things difficult, then you find things that are true functional equivalent that are conditionals and negations, and it's more likely to be difficult to understand. Another practical application is when designing, say, circuits or like a program, there may be things that would be more efficient way to do it, using things that are true functionally equivalent. And so there can be reasons when designing a circuit or something for simplicity or ease, or if you just happen to be limited by what you've got to work with, where that can be something to do. So here's a simple example of two claims that are truth functionally equivalent. And sometimes it can seem kind of surprising because the claims may seem to be nothing alike, but then when you do the truth table for them, you can see that they actually are true functionally equivalent. So our example of this, there are many claims that are true functionally equivalent, but in this case we've got if P then Q, and we also have not P or Q. And again, this may seem odd to say that they're true functionally equivalent. They mean the same thing informally. They do mean the same thing. So, for example, to use a concrete example, if we say if Sally passes the final, then she passes the course, it may not seem to say the same thing as either Sally will fail the final, not pass the final, or she'll pass the course. And one's a one's a disjunction, one's a conditional, but they actually do mean the same thing. And this can be proven. So in order to prove that if P then Q and not P or Q are true functional equivalent, we of course build a truth table. So as always, we just have the two variables here, so they live on the left side of the table. We begin with P, followed up by Q. Again, just tradition and convention. We start off with the rightmost variable, which is Q, and we alternate singles, TF, TF, and we have, of course, two variables, so the table will be have a number of rows equal to 2 to the 2, so 4. Then we head to the left, alternating, pairs, TT, FF, and then we fill up the table, and then we're done with that part. Then we fill in the rest. So we need not P for the not P or Q, and so we put in not P, we give it its own column. Traditionally, usually negated single variables are typically put close to the variables that have just plain variables, just because it's easier. You can put them in other places, but generally it's easier to do so. Not wrong to have them another place, but easier. So not P is the negation of P. So true, true, false, false becomes false, false, true, true. In this case, P then Q fills in just like our example simple table. It's a conditional, so it's going to be true except when the antecedent is true and the consequent is false. So true, false, true, true. Now in the case of not P or Q, to see why this fills in correctly, it's a disjunction, so it's true except when both of them are false. So this will be true except when not P is false and Q is false. And of course not P will be false when P is true. So we look at the not P column, we look at the Q column, and if there's a true in either one of those or both, then not P or Q is true. So not P in the first row, not P is false, Q is true, so not P or Q is true. Then going down to the second row, not P is false, Q is false, and so not P or Q is false, because it's a disjunction with two false disjuncts. Then going down to the third row, we have not P true, we have Q true, so both are true, so the whole claim not P or Q is true. And then we get to the last row, not P is true, Q is false, but that's fine, because only one of them has to be true, so not P or Q would be true. So they're shown to be true functionally equivalent. Now, the only connective where the order matters is the conditional. If you have P or Q, and if you have Q or not P, it doesn't matter. There's not like a separate table, separate column for that. And so and or order doesn't matter because there's no reference to order. But with the conditional, if P then Q, the order does matter. Now, in everyday language, of course, the order of things can matter. So, for example, if we take true functionally the claim Dave put on his boots and Dave walked across the broken glass, that is true function equivalent to Dave walked across a broken glass and Dave put on his boots. They true function are the same. But of course, in outside of true functional logic, temporal order matters. And we usually reference, order by putting one, ahead of the other. But again, true functionally doesn't matter, because technically it's true that both were done. Now we turn to symbolizing compound claims. So the objective is to get from normal or semi-normal English, or whatever language one is using, to get into true functional form. And true functional standard form can't have any words in it. It has to have only claim variables like P, Q, and R, connectives, and parentheses. Only three things that can be in there. If there's still words left, it's not in standard form. So how do we do these translations? Well, not surprisingly, the conditionals are typically the toughest to translate. Something like translating it's not Tuesday, that's real easy. You just make P Tuesday and that would be not P. And and or also tend to be pretty easy to translate. The conditional, though, because they've got if, that becomes, as we'll see, kind of problematic. How so? Well, we've got if, we've got only if, and only if. You might recall from the categorical logic, we had only and the only, and so only is back to mess with us. Only in this context, it's the conditionals. So here is the way to decode, normal English into standard form. So if, by itself, assuming the person's, following the rules of logic, it always introduces the antecedent of a conditional, regardless of where it occurs. So one thing about, English, maybe other languages too, is you can put your antecedent, later. But the giveaway is if it's if by itself, that always grabs the antecedent. So, for example, Sam will buy the popcorn if Sally buys the tickets. That is saying that if Sally buys the tickets, then Sam will buy the popcorn. So we have, P, comma, if Q would be, in this case, Q then P. Assuming that we've got, Sally buying the tickets as Q, P being Sam will buy the popcorn. Only if gives us the consequent of a conditional. So if we have if by itself, that gives us the antecedent. If we have only if, it gives us the consequent. So Sam will buy the popcorn only if Sally buys the tickets. This becomes if Sam buys the popcorn, then Sally buys the tickets. So P only if Q would be equal to if P then Q. Now, when people are talking normally, they're often not super careful about only if and if, etc. And so sometimes you have to go by context to see what the person actually intends. Now, of course, we can combine if with only if, getting the if and only if, so beloved and often used by philosophers. So what if and only if becomes is both of those. So if we say Sam will go if and only if Sally goes, we're saying two things. We're saying if Sam goes, then Sally will go. And we're saying if Sally goes, then Sam will go. So P, if and only if Q, becomes if P then Q, in parentheses, and if Q then P, in parentheses. So that's the translations. So if always gives us the antecedent of the conditional when it's by itself. Only if gives us the consequent of the conditional. If and only if gives us, both of those going on, gives us that more complicated sentence. Some logic books have the if and only if they have what's called the material biconditional, which gets its own symbol, but for some reason the authors of this book didn't include that. They just stick with the conditional. Now, in accord with the ancient tradition of teaching logic, we must of course talk about the necessary and sufficient conditions. So here's how to translate necessary and sufficient conditions. A necessary condition is this. To say that A is necessary for B, whatever it might be, is to say if A is the case, then B can be the case. Or alternatively, if A is not the case, then B cannot be the case. It can be seen as like a requirement. So if taking, chemistry 1 is necessary for taking chemistry 2, that means if you took chemistry 1, you could take chemistry 2. And if you didn't take chemistry 1, then you can't take chemistry 2. Now, in terms of how this translates into a conditional, the necessary condition will be the consequent of a conditional. So, for example, if we say that oxygen is necessary for human life, then that means, translated, would be if there is human life, then there is oxygen. So to say that P is necessary for Q would be Q then P. Or if we say that Q is necessary for P, we would reverse that, of course. Going back to only if gives us a necessary condition. So if someone says, you can take chemistry 2 only if you've passed chemistry 1, they're giving the necessary condition. Now to the sufficient condition. A sufficient condition is, as the name states, sufficient. That's to say, it can bring about what it's sufficient for by itself. But kind of talking causally. So if we say that A is sufficient for B, we're saying that if A is the case, then B must be the case. And the sufficient condition gives you the antecedent of a conditional. So if we say that being born in the United States is sufficient for being a U.S. citizen, that would translate as, if a person is born in the United States, then they will be a citizen. So if we say that P is sufficient for Q, we would say if P, then Q. Or as another example, if we say that earning a 60 or better is sufficient to pass this class, would be if a person earns a 60 or better, then they pass the class. Or whatever the grade required is. Now, since necessary and sufficient conditions give us the only if and if, not surprisingly, we can combine them into the necessary and sufficient conditions. So, if A is necessary and sufficient for B, then B cannot occur without A, the necessary part, and if A occurs, then B must occur, the sufficient part. And it's typically expressed as P if and only if Q. And the symbolization is, as we saw, if P then Q, P arrow Q within parentheses, and then ampersand, Q then P also in parentheses. For example, as an everyday language example, a person is a bachelor if and only if he is an unmarried man, and that becomes if a person is a bachelor, then he is an unmarried man, and if a person is an unmarried man, then he is a bachelor. And so P is necessary sufficient for Q ends up being symbolized like shown here. Now, philosophically speaking, the necessary and sufficient conditions are often seen as kind of the perfect definitions. If you could provide the necessary and sufficient conditions for defining, say, art, you would know such that if something has these qualities, meets these conditions, then it would be art. And if something doesn't meet those conditions, it wouldn't be art. You'd have a perfect definition. And as you might imagine, we generally only have perfect definitions for things that are pretty simple concepts like being a bachelor or being a triangle. Now, continuing our adventures in conditionals, as I noted before, people, when they use ordinary language, they're often not super careful. They have an intent, but their words don't always match up with that. So, for example, a parent might tell their child, you can watch television only if you clean your room, which is something that would typically be said. Now, what is actually being expressed here is only a necessary condition. So what the person is intending to say is that it's supposed to be that if the child cleans the room, then they get to watch television. But technically speaking, by using only if, what the parent is saying is, if the child is watching television, then they have cleaned their room. So logically speaking, the child could clean their room, making that true, but they may not be allowed to watch television, because then it would be a conditional, if watch television, then clean the room. And of course, the consequent could be true and the antecedent false. But when people are talking, normally, we go by their likely intent, as opposed to does it exactly match logic. Now, as a practical matter, of course, any exams, quizzes, and assignments, the assumption will be that it's being used, I don't want to say correctly, but being used technically. So you can watch television only if you clean your room would logically translate to if television, if they're watching television, then the room has been cleaned. So you won't have to rely on normal interpretations and just go with what the logic says. Last bits of translation, not really tricks, but kind of methods. So the word unless also creates some confusion because it's got a conditional, potentially, and of course negation in there. And the game section of the LSAT makes extensive use of unless claims because, again, they combine conditionals and negations, and people are generally bad at that, so it maximizes confusion. So how do we translate P unless Q? Well, this translates as if not Q, then P, which by the going back to truth functional equivalence, this may sound kind of odd, but not Q, then P is the same thing as P or Q. So one handy use of this, if you're taking the LSAT, for example, or dealing with a conditional like not Q, then P, is you can convert it to something that's probably easier to handle, which is just P or Q. And again, this may seem odd, but it's actually a correct true functional equivalence. So, for example, Bill will go unless Sally goes would translate as if Sally does not go, then Bill will go, and this becomes Sally will go or Bill will go. And you can do the truth table to see that this is correct. Lastly, either. So we move away from conditionals to a disjunction and conjunctions. So either works like this. So if we have either P and Q, that will give us a disjunction with a conjunction in there. If we have either P and Q or R, the either tells us like which part belongs in the parentheses. So either P and Q or R, by kind of the rules of English, becomes P and Q together or R. So you have either P and Q or R, and that would be the translation. So for example, if somebody says that there'll be cake and ice cream or pie, that means there'll be cake and ice cream together, or there'll be pie. Of course, possibly both, because it's a disjunction. If we have P and either Q or R, that would be P and the parentheses would be around the Q or R. So even though we have the same parts, P and Q or R, the either tells us where the parentheses go. So that would be having, say, we'll have cake and ice cream or pie. So that would be the difference in the meaning. So that takes the end of the basics of translations, and in our next class and final class, we'll finish up truth functional logic. So stay safe, and I'll see you in the future.